Hello to everyone here on campus at the University of Michigan and to those watching our live stream. Welcome to Saturday Morning Physics and to this special event. Well, actually, all our events are special, but this one is especially special because we have today two graduate students presenting their cutting-edge research to us, so we're really looking forward to that. This is also our last Saturday Morning Physics event of the academic year, as the winter term is winding down. So I'd like to take a moment to thank and have you help me thank some of the people who make this possible. And first, I want to start with Carol Raybuck, who greets you and is really the chief organizer of this event. So thanks so much, Carol. And I also want to acknowledge and thank Monica Wood here, who runs the demo lab. And as you've all seen, does so much to make these possible. And her staff of Nick Arnold and Connor Heaney of the demo lab here. And they also prepare these demos, do the technical things. And I also want to acknowledge and thank the video production crew that's led by Carl Cole. And he's in the back of the room here all the time. I can't see him. Did you take a bow, Carl? He always makes a production of it. And also, thanks to Sarah Mallon and Rosemarie Gross-Plouffe, who also greet you in the back and help do the publicity and organization, et cetera, and welcome you. And thanks to all of you for joining us here, and also for your support of Saturday Morning Physics, both by joining us here and online and with your financial contributions. That is what keeps Saturday Morning Physics going and so popular. I am physics professor Tim Chupp, and it's been my privilege to host most of these events and be one of the faculty organizers, along with Professor Rachel Goldman. She can't be here today, but her thoughts are with her and her family. Before moving on, I just want to note that we will have the question and answer period at the end of the presentations today, the two presentations. And for those online, and even for those here, though we will have microphones, a microphone here for you to ask questions, those who are here in the room, but also you can email your questions to physics@umich.edu. So it's really great to have this Van Loo family graduate student lectures every year. Today we have two graduate students, both in physics, Emilie LaVoie-Ingram and Otávio Alves. Emilie, who actually gave the first talk, is actually formally joining our PhD program in physics this fall, but she's been working for the past year with Professor Josh Spitz, who's here in the audience. She's from Chattanooga, Tennessee. And she did graduate study in materials science and got a master's degree from the University of North Florida, and then worked in industry doing electromagnetic simulations in Denver before she started working with Professor Spitz on the research she'll tell us about today. And he, recognizing her talent and promise, was recruited to our PhD program and will be joining that in the fall to work for a PhD in physics. Emilie is very much at home, and she's dedicated to public outreach, and she's a certified, I think that's the right term, science communicator, having been trained. Yes, and she's tireless at this, and in fact, after she presents and answers your questions here today, she'll be going over to the Natural History Museum for the Scientist Spotlight to present her work there. So you or probably be invited to join that as well. Otávio Alves is a PhD student in physics here at the University of Michigan. He works with Professor Dragan Huterer, who is also here. Otávio is born and he grew up in Brazil, graduated from the Federal University in Minas Gerais. Yes, thank you very much, Minas Gerais. I have to go through this pronunciation training, but I'm still not very good at it. He had a master's degree in physics from the Institute of Theoretical Physics before coming to the University of Michigan to join the physics PhD program here. So Emilie is up first. She'll tell us about digging up dark matter with paleo-detectors. Emilie.
All right, thank you, Tim. All right, good morning, everyone. So what if I told you that this rock that's in my hand holds clues to the universe's most intriguing mystery, the nature of dark matter? Now, from face value, that sounds kind of like sci-fi, but today I'm very excited to tell you exactly how we can do this using something called paleo-detectors. But before we get to that detail, we need to talk about the big picture. So let's discuss our universe. So for decades, physicists have been constructing a map of what we know about the observable universe. We call this the Standard Model. Now, the Standard Model is comprised of our fundamental particles. They are broken up into our fermions, which are our particles of matter, and our bosons, which are our force carrier particles. Now, the Standard Model does a really great job at explaining what we know about normal matter, and it's a very powerful tool. But there's one glaring problem. It technically doesn't account for most of what the universe is made of, and that, my friends, is something called dark matter. So dark matter is a word for this invisible mass that we infer is there based on its gravitational effect on normal matter. Now, normal matter is what makes up things like stars and planets and you and me and your dog and the donut you ate this morning. And one of the more striking pieces of evidence that we have for the existence of this dark matter is what you can see on the left of the slide. So this is a picture of the bullet cluster. This is a remnant of two galaxy clusters that collided about 100 million years ago. And what you can see in the pink, this is all the hot gas, which is most of the normal matter, detected with X-rays. And what you can see in the blue, this is the distribution of most of the mass in these galaxy clusters. Now, that's determined with something called gravitational lensing, which you can think of as the way that light is bent from the background galaxies, from the mass in the foreground. It tells you where the mass is, but not what the mass is made of. So by looking at this, looking at the bullet cluster, we can see a couple of things. First, most of the normal matter, all the pink stuff, that hot gas during the collision interacted with each other and slowed down, which is why it's all clumped up in the center. Now, most of what these galaxy clusters were made of, the stuff that's detected in blue, seem to have passed right through each other, not interacting at all. Now, this is key evidence for some sort of invisible mass that we can't seem to interact with right now. And there have been many more observations just like the bullet cluster, and so nowadays, we can safely say that dark matter makes up a whopping 27% of the mass energy distribution of the entire universe. Now, it is 5 times more abundant than normal matter. And so when do we kind of start to see the first key pieces of evidence of this? Now, to answer that question, we have to go back nearly a century. Now, technically, it was Fritz Zwicky back in 1933 that detected the first piece of evidence for this invisible mass. And he named this dunkle Materie, which is the German word for dark matter. Now, it wasn't until the 1970s when 2 scientists, Vera Rubin and Ken Ford, established the hypothesis of dark matter. And they did this by measuring something called a galaxy rotation curve. And so they did this for a bunch of spiral galaxies. And a rotation curve is a measure of a star's velocity as a function of distance from the galaxy center. Now, what we expect is as stars go further away from the center of galaxy, they're going to decrease in speed. And you can see this in the top right as a qualitative plot. And we can calculate this pretty simply by using something called centripetal force, which is the force felt by an object moving in a circular orbit, set that equal to Newton's law of universal gravitation, and solve for velocity. Now, this is not in any way what they observed. In fact, they found that the stars at the edge of these spiral galaxies were rotating just as fast as the stars near the center. And you can see a simulation to show this dramatic effect. So this stumped physicists, And so nowadays, there are a ton of theories out there trying to figure out what dark matter could be. And there's one in particular I want to point out, and so this is the theory that paleo-detector research is based in. And we call that the weakly interacting massive particle, or WIMP for short. So this is a particle-based theory of dark matter. We assume that if this particle existed, it's going to interact via gravity, aka have mass, and also the weak force. So the weak force, it was kind of mentioned on the standard model side, you can think of as accredited to certain types of radioactive decay. You can essentially transfer energy from one particle to another or change its type. Now, the mass of a WIMP particle we predict to be in the giga-electron volt range. So this is 1 billion electron volts. And that's about 2,000 times larger than the mass of an electron. Now, we also know that if these WIMPs existed, there would be a very small probability that they would interact with normal matter. Now, when a physicist hears that, they're thinking, okay, so you're telling me there's a chance. And so nowadays, there are a ton of different direct detection experiments going on trying to discover what dark matter could be. Now, there are 3 ways that you can approach these detection experiments. The first is collider experiments, here in the pink. So in these experiments, you assume that a standard model particle, which is what SM represents in this diagram, and another standard model particle can collide with a high enough energy and produce a new exotic particle like dark matter. Now, the second way is indirect detection. Here you assume that 2 dark matter particles can annihilate and create a particle that we know exists, part of the standard model. And the third is direct detection. This is what paleo research is based in. And this is when we assume a standard model particle and a dark matter particle can interact. And the dark matter particle is going to kick the standard model particle a little bit. It's going to give it some energy. And it's that change in energy that we can measure. And so there are many experiments that are based on this concept of direct detection. I have here listed 2 of very famous ones. So the top one is the LZ, the Lux Zeppelin experiment. This is a liquid xenon experiment based deep underground in South Dakota. In the bottom, this is Deep 3600. This is a liquid argon-based experiment deep underground in Canada. Now, both of these experiments and many more are built on this concept of exposure. And you can think of exposure as mass multiplied by time. Now, they have these enormous masses to make up for the fact that they are detecting in real time to catch such a rare interaction between dark matter and normal matter. Now, ultimately, there is a limit in how large a mass we can go and also how long we're willing to wait. And so I pose you the question, as an alternative, what if instead we could look back in time? And so this is where the concept of paleo-detectors come in. So paleo-detectors are ancient minerals that can preserve track-like defects induced by nuclear recoils caused by particles, including the theoretical dark matter particle. Now, these recoil tracks, these damage tracks, are on the nanometer scale. You can see an image of them over on the right. So in width and diameter, they're only a couple of nanometers. In length, our observable goes all the way up to a millimeter. But the real kicker is that these tracks can be preserved for billions of years. They are quite literally a cosmic time capsule right underneath our feet. And so we are instead getting our exposure through time, as compared to the experiments previously. And so to give you perspective, this rock is 115 grams, and it's 1.2 billion years old. So this rock in my hand has more exposure than a 10 kiloton experiment operating for a decade. Enormous amount of potential. Now, before we get into the details of that, let's first talk about how these defects are created in the first place. So the creation of a track first starts when a particle enters a crystal lattice and it interacts with an atomic nucleus. That interaction transfers energy to that nucleus, and it causes it to recoil through the lattice, and along its trajectory, it's going to locally ionize, or in other words, displace charges, creating a string of vacancies with a shell of interstitial atoms. Now, a vacancy is an empty lattice site. It is a space where an atom is missing. And an interstitial atom is an atom that is shoved in a lattice site that it shouldn't be in. So, fun fact, for every vacancy, there's an interstitial pair, and we call those Frankel pairs. And so there's a really neat demo that we can do to watch these tracks in real time. And that's with something called a cloud chamber. And that is actually sitting right behind this table. It is a real thing. And so this will come up in just a moment, and I'll explain to you what you're looking at. It's a very neat thing to watch. So what you're seeing is a chamber of supersaturated alcohol vapor. Now, this is alcohol in the gas phase that is right on the border of being in the liquid phase. And so it takes just a tiny bit amount of energy to cause that gas to condense into droplets. Now, the rod that you see in the center, this is a thorium-doped welding rod. Thorium is radioactive, and so it's emitting ionizing particles. Those particles include alpha particles. This is a helium nucleus. It is 2 protons and 2 neutrons. It is also emitting beta particles, these are electrons or positrons, as well as gamma rays, which can convert into an electron or an electron-positron pair by interacting with the electric field of an atom. Now, these tracks all have distinct shapes, and so I've created a guide so you guys can do some track identification in real time. So alpha tracks come out as straight, long tracks directly off the rod. Beta particles have these long, kind of swoopy, curvy tracks, and that's because the electron is being pulled by the induced magnetic field. And then gamma ray tracks, you're actually not seeing the track from the gamma ray itself. You're seeing either the single electron track, which is going to be kind of these little wispy feather-like tracks, or going to be Y-shaped tracks, which is going to be the electron-positron pair. Now, I'll let you guys look at this for a few more seconds, and I'm saying that mostly because I want to watch it. And then I want to talk about something called radioactive decay that I just mentioned with the thorium. Definitely a lot of variety. Now, this thorium on this rod, as awesome it is to watch, this ends up being a problematic process for paleo-detectors. And so I want to talk about this for a little bit. So I mentioned when I introduced paleo-detectors that different particles can induce tracks. And we call those other particles besides dark matter backgrounds. And so a big source of backgrounds are going to be particles induced from radiogenic processes, and there's 2 we have to take into account. The first is radioactive decay. This is the natural decay chain of heavy radioactive elements like thorium. The most common is going to be uranium. And so during that process, this heavy nucleus is going to emit an alpha particle, and a heavy nucleus is going to remain. And that's going to keep decaying all the way until it gets into a stable element. Uranium-238, this is the most common mineral or most common radioactive element you're going to find in natural minerals. This eventually will decay all the way to lead-206, which is stable. But the other process that we need to take into account is spontaneous fission. This is when a heavy element captures a free neutron, and it instantly becomes unstable. And so the instability causes the atom to rip apart into 2 different nuclei, and it emits both the recoiling daughters as well as a bunch of free neutrons that we call fast neutrons. Now, I'm going to talk about fast neutrons in a couple of slides, but there's actually a really neat way that we can test if a rock is radioactive in real time. So, if a rock is radioactive, it's going to be actively emitting ionizing particles. And what you're going to see on the screen very briefly are going to be 2 rocks. Now, these rocks look not very distinct from one another. So they kind of just look like rocks you can get out of your backyard. But if, so to say, one of these rocks is radioactive, it's going to be emitting those ionizing particles, and there's a really neat instrument we call a Geiger counter that we can use to detect those ionizing particles, and it's because they enter this tube, there's gas in this tube, and when they interact with that gas, they create an electric pulse, and we're going to hear that as a popping sound here. So I'm going to turn this Geiger counter on, and you're going to quickly start to hear this popping noise. Now, this is not because the room itself is radioactive, I promise. You're actually hearing the cosmic ray background. And I'm going to talk about this next, so you can just put that in your back pocket for now. But what I can do is I can hold this Geiger counter above one of these rocks and see if any of them are radioactive. And it might be obvious by now that one of these is going to cause the Geiger counter to beep, but I want to assure you are completely safe. I mean, just don't eat the radioactive rock and you'll be completely safe. But if I hold it across, this first rock, I don't really hear any more beeping other than the background noise. Maybe something. But if I hold it over this rock, right, right, safe to say that one's a little bit more exciting. So this rock on what would technically be your right is a radioactive rock. It is a mineral called columbite, and it's from Colorado, and it's very rich in uranium. Now, this is an example of how one rock could be a lot better than the other when choosing a paleo-detector mineral to use. So one rock has a lot of radioactive concentration, it's going to have a lot more background tracks, and another will not. Now, this is not the last time I'm going to use our favorite little radioactive rock, but for now, I want to change topics and talk about this beeping I mentioned with the Geiger counter. So when I first turned it on, I said that you're hearing a background of cosmic rays. So let's talk about those for a second. So cosmic rays are mainly protons coming from outer space, both inside and outside our galaxy. And when these protons enter Earth's atmosphere, they create a shower of charged particles. And those charged particles, like the muon, for example, can interact with matter in Earth's crust and produce a bunch of energetic particles called fast neutrons. Now, these fast neutrons, to be completely blunt, are very annoying. They can penetrate through meters of rock and interact between 10 to 10,000 times before coming to a stop. In other words, these induce a lot of tracks. Now, there's a good reason, or there's a way that we can avoid these problematic particles, and that's by going deep underground, and we call this shielding from cosmic rays. So I'd like to demonstrate this for you today. So I am going to come back and find our favorite rock, and I'm going to turn on our Geiger counter, and you're going to start to hear that beeping. Now I'm going to do a super quick magic trick. So we know that this rock is emitting radiation from its radioactive decay, but now we're going to pretend it is a muon emitter. And so this Geiger counter is going to detect the muon flux that we're going to say is at sea level. Goes crazy. And what I have in front of you are 3 different kinds of shielding. So I first have a piece of paper. So as you can imagine, this piece of paper is probably not going to do much. So I'm going to say this is like going 1 foot underground. Now, just to remind you, a lot of radiation. If I go through the piece of paper, a lot of radiation. Now, what I have next to it is a piece of wood. Now, it's the same material as paper, but this piece of wood is 500 times more thick than the piece of paper, so I'm going to say this is like going 500 feet underground. Now, if I hold this target between the piece of wood, might take just a second, but you can still hear a decent amount of radiation. Some of that's from background. A lot of that's coming from the muon emitter. Now, what I have next to it is a piece of lead. This lead brick is just as thick as the wood block, but it's 20 times more dense than the wood. So this would be like going 10,000 feet underground. Now, if I hold this, sometimes it takes a second to quiet down, but you're going to hear a lot less tracks, or a lot less beeps, so to say. But in the real world, it would be a lot less tracks. So what we can see from this demonstration is that the deeper you go underground, the more shielded you are from the cosmic rays. And so this gives us a good clue of the types of rocks that we want to look for whenever we find a paleo-detector. Now, we've learned a lot so far. We've learned that dark matter can induce tracks, radioactive ionizing particles can induce tracks, and cosmic rays can induce tracks. So what we can do with the information is construct a list of what we think the ideal paleo-detector would be. And so there are 5 main points I'd like to touch on whenever I talk about the perfect rock. The first is that, above all, we need it to be very, very old. We talked about exposure earlier. In order to find these preserved rare interactions, we need it to be old enough to capture them in the first place. So for dark matter detectors, we look for rocks that are at least 1 billion years old. On top of forming 1 billion years ago, we also need to make sure they've been preserved for that amount of time. So we also need to make sure it's robust against a process called annealing. Annealing is a recrystallization of a lattice. It erases defects. This is a bad thing. We want the defects to stay there. So in that case, we look for rock formations that have stayed under a few hundred degrees Celsius throughout their lifetime, and that's because that's about the threshold when minerals start to anneal. Now the third, we just learned about radioactive decay, how that can induce tracks. To mitigate this, we can find rocks that naturally have a very low concentration of radioactive elements. And for us, that's typically less than 0.01 parts per billion. Now, we also just saw that shielding helps mitigate the cosmic rays, and we can do that by going deeper underground. So our next point is to go deep into Earth's crust to find these minerals. Now, to completely mitigate the cosmic ray background, we can go about 5 kilometers deep. That is 16,500 feet underground, or 13.5 kilometers water equivalent. Now, kilometers water equivalent is the amount of water it would take to have the same shielding as a certain overburden of rock. So it takes 13.5 kilometers of water to reach the same amount of shielding as 5 kilometers of rock. Now, if all 4 of these points were not strict enough, we also need to make sure that these rocks have been freshly extracted, or in other words, freshly brought to the surface. And that's to avoid the sea level cosmic ray flux. So taking into account these 5 points, we have determined 4 paleo-detectors that we think are really great rocks to use. Now, the first of which is olivine. Olivine is noted for its bright green color. It is a magnesium or iron-based silicate material, and it's the most abundant mineral on Earth. Now, the second is quartz. Quartz makes up most of the sand that you sit on when you go to the beach. It's silicon dioxide. Now, we also have halite. Halite is sodium chloride. It is rock salt. Now, you can, in fact, eat this rock. You probably eat this rock every single day, and if you don't, I'm sorry, your food's probably very bland. But this is a rock I used quite a bit during my master's research. It's a neat one to use. And last but not least, and certainly not least expensive, is diamond. Diamond is pure carbon, and that carbon's locked together securely in covalent bonds, and it's the strongest mineral on Earth. Now, once we put together a list of the minerals that we want to use, we then have to go find them, and I can say I've had quite a fun time doing that so far. So this is a kind of sample of some of my favorite rocks in Michigan's collection, and a lot of them are from all over the world, very deep, and I've also had the opportunity to collect some of them firsthand, and so you'll notice on the left of the slide, these are a couple pictures of me in 2 different mines in Canada. Very fun experience. Now, the quartz that you see here, these 3 pieces that are kind of free-floating, these are all from Canada. The leftmost 2 are 1.2 billion years old. The one in the center is 2.7 billion years old. And the other rocks that I'd like to point out, and I can't explain too in depth for the sake of time, are these 3 that kind of look slightly boring, but I assure you that they're not. Now, within them are these teeny tiny olivine grains that are 3.5 billion years old. So to give you perspective, the Earth is about 4.5 billion years old. These are very, very old rocks. So I'm very excited to look at these. I got these about 5 days ago. And they're very special not only because they have this insane exposure for dark matter detection, but they're very special for something called atmospheric neutrino detection. And I didn't mention neutrino detection at all, but we can also detect neutrinos. So if you're curious, feel free to ask me during Q&A. But as fun as it is to go out in the field and find some cool rocks, there are also some pitfalls associated with working with natural minerals. I often like to say this is like opening Pandora's box with 1 challenge, 5 follow. And there are a couple of these I would like to point out because they're pretty significant for us. Now, the first is an uncertainty in mineral age. Whenever you date rocks, you typically use the radioactive concentration. You either count fission tracks directly, or you count the amount of a stable isotope that would only be there because of radioactive decay. Either method relies on you having a lot of radioactive concentration, but I mentioned earlier we don't want that. So this can often, end up having a lot of uncertainty in our age. There are ways to mitigate this, of course. But another one I'd like to highlight is this uncertainty of depth and thermal history over time. So the Earth is very dynamic. We're sitting on a molten mantle, and that's moving the crust around, and there are all volcanic eruptions and plate tectonics, and rocks are recycled and heated up, and that's all things that we don't want because we want these rocks to be preserved. And so sometimes it can be very difficult to determine whether a mineral I found at 3 kilometers deep formed at that depth, or if it was buried over time, or if it's been at 1 kilometer for half its life and 3 kilometers for the second half of its life. Who knows? This often kind of relies in us doing a lot of literature review with places that geologists have studied. Helps mitigate the uncertainty. It's a very interrelated field with geology, if you can't tell. But another way that we can help mitigate these challenges, another way we're overcoming these challenges, is by doing some really neat studies here at the University of Michigan. So one way that we can study our minerals and study how tracks form in our minerals is by using some tools and techniques that help us find them in the first place. Now, a couple of these, we first have transmission electron microscopy. This does exactly what the name says. It transmits electrons through a thin piece of your sample, and you essentially get a 2D projection of the 3D internal structure. And so as an example, this image in the center is a TEM, or transmission electron microscopy image of ion tracks, which I'll explain that in a second, in a mineral olivine. Now, we also have an ion beam on campus. This is very useful. Most campuses don't. You can see that in the upper right. Now, an ion beam allows us to implant ions, which are like charged atoms, into our sample, and those can induce tracks. So what we can do is we can use those to induce tracks we expect to see naturally. We can study how those tracks form and how they morph in our target minerals. Now, another thing that I'll kind of point out is in the center image, there are hundreds of tracks here, and we collect thousands of these images, and it would be nearly impossible if I sat there and hand counted and hand measured all of them. And so one thing that we can do to help with that process is create an automatic track detection algorithm, which is what you can see in this bottom right. So AI and machine learning end up having a pretty important role in our research. It's kind of a neat topic, but something I want to mention about TEM is it's a very strong tool. It gives us incredible resolution, and we can see these tracks quite clearly in the center image, but there are a couple downsides. So a TEM image takes, maybe a couple of minutes to render, but I want to give you a perspective of the size of this image. So this is about a 1 micron by 1 micron image. This is 20 times smaller than the width of one strand of your hair. This is tiny. The entire sample that this is from is about 20 microns by 20 microns by 200 nanometers. We can image that entire sample in maybe about 4 hours. That's not including the sample prep to get such a small sample. So if you do the math, to image, for example, 1 gram of rock, which we consider our minimum amounts of rock that we need to analyze for a measurement, so just kind of like a flake of this, 1% of this rock, it would take 1 billion hours, over 1 billion hours, actually. And I know PhD students are notorious for grinding away in the lab, but I certainly do not have 1 billion hours to spare. And so one way that we can transition from TEM is by using X-rays. Now, X-rays are wonderful because they have a higher throughput than TEM. Throughput means the amount of something that you measure in a certain amount of time. So we can scan more material quickly with an X-ray than we can a TEM. But the downside is that X-rays have a longer wavelength than electrons, so we're losing resolution. In fact, the best resolution is about 15 nanometers that we expect with X-rays on our minerals. Now, to give you perspective, a TEM is sub-nanometer. You can see individual atoms with a TEM. Now, our natural tracks are on the order of a couple nanometers wide, so already an order of magnitude lower than the highest resolution we expect to get, but they're quite long. So it's not dead in the water. We just won't be able to see the tracks as clearly as you do with a TEM. Now, we are waiting on a brand new X-ray microscope to be delivered here at the University of Michigan. Very excited to get started on it. But in the meantime, what we can do while we wait for that is use other X-ray sources. So, for example, 2 weeks ago, I was at the Stanford Linear Accelerator Center, otherwise known as SLAC. And this was our first proof of concept study imaging tracks with X-rays. So we used an imaging technique called transmission X-ray microscopy. So it's essentially kind of the same methods of a TEM, but instead of electrons, you have X-rays. And so the images that you see in the bottom right of these tracks are much larger than the natural tracks we expect to find. And that's because we knew with this particular beam, we were not going to see down to the tens of nanometers level that we were hoping to. But what we can do with this data is we can image these artificial tracks that we created and say this is what we can see with X-rays, this is what we can't see with X-rays, and this is what we really want to see. And we package that up into a proposal, and we ask better light sources like the light source at Argonne National Lab or the Swiss light source and we say, pretty please, with a cherry on top, can we have some beam time? And so there will be some hopefully very exciting things in the future. And I'm definitely excited to see where this research goes. And so just to start wrapping up, if I leave you with anything today, I want you to remember that paleo-detectors are cosmic time capsules sitting beneath your feet. And they have been recording remnants of dark matter interactions for billions of years. Now, I can't fully end without thanking the wonderful team at the University of Michigan. So we have 3 great PIs. Josh is my personal advisor. We also have Kai and Igor, a grad student, Cassie, and 2 undergrads, Katie and Andrew. They all work tremendously hard. We also have collaborators all around the world. And one last thing, Tim mentioned this earlier. I will have a booth at the Scientist Spotlight at the museum later today from 2 to 4, so feel free to stop by. That's all I have for you guys today, so thank you.
Thanks, Emilie. Emilie will be back for the question and answer session after Otávio's talk. So next up is Otávio. We practiced this. Otávio will tell us about the Dark Energy Spectroscopy Instrument, or DESI. I think that's the right way to pronounce it. All set? Otávio Alves.
All right, can you hear me well? Is this on? Amazing. So thank you very much. Today, I'll be telling you about the Dark Energy Spectroscopic Instrument, or DESI for short, and how we use it to study dark energy. So I'll start with a question. So you might have heard that our universe is expanding. But what does that exactly mean? Is it expanding like an inflating balloon? Is it like a cake you have in the oven? You might have heard some of those analogies, but I wanted to give you a slightly more precise definition of the expansion of space-time. So, to start, 200 years ago, we used to think space was this flat and boring thing. Things that exist in space, they move around and do tricks, but space itself is static, doesn't do anything. But in 1915, Einstein published his theory of general relativity, proposing that space-time, so not space and time independently, but now this entity that is called space-time, can curve and bend. It's a dynamical thing, just like a fabric. That can be sometimes very counterintuitive. But when intuition fails, we have tools to help us understand things beyond our own intuitions. And that's why I wanted to give you a mathematical description of space-time. Mathematics is always there to the rescue. So in mathematical language, space is a set of points. And each point has points to its left, points to its right. So there is a notion of neighborhood in this space. And in addition to that, we specify a method to calculate distances. So we need a way to calculate distances between these points, and that's what we call the metric. And the metric I have there at the bottom, that mathematical formula, should be familiar to many of you. I think we studied that in high school, at least in Brazil we do. And the Greeks knew that already, thousands of years ago, right? Because that comes essentially from Pythagoras. So if you have 2 points, first you label your points by x, y, and z coordinates. And then if you want to estimate the distance between these 2 points, what you do is you calculate the difference in the x coordinate, delta x, right? Distance in the y coordinate, delta y. And then to get the distance between the 2 points d, what you do is you square those deltas and add them together. If you are in 3 dimensions, you have an extra coordinate z that you add to that equation. Great. This is the simplest metric that we usually see, but that's not what describes our universe in large scales. The metric that best describes our universe in cosmological scales was first discovered by Friedman and Lemaitre, and then further studied by Robertson and Walker, and is given by that expression there on the slide. Part of this expression is already familiar to you, the deltas squared. But you see now that this part of the equation is multiplied by a function a function of time. And this function is what we call the scale factor, because it is scaling all distances in our universe. So the distance between any 2 points in this set of points is being multiplied by this number. If this number is greater than 1, distances are increasing. If this number is smaller than 1, distances are smaller than what we would expect. So the behavior of this scale factor looks like this. So here in this plot, I have time in the horizontal axis in billions of years. And in the y-axis, we have a, the scale factor. If you move to the left, so scale factor is 1 today by convention. But if you move to the left, all the way until you hit 0 here, you see that all the distances, they get infinitely small. So everything was infinitely close to each other at the beginning of the universe. That's the point what we call the Big Bang. And from that point, the universe starts expanding, so all the distances increase over time, including the distance between me and Dragan right now. But fortunately, there is concrete to keep us together here so we can still chat and figure out what dark energy is. But for galaxies that are far away, we don't have concrete holding us together. Not even gravity can do that. So for galaxies far away, we'll keep seeing them moving further and further away. So space-time, the universe, is not only expanding, but its expansion is accelerating. That's something we have known now for more than 20 years. And there are really these two key papers that show this in 1998 by studying light from supernovae. Supernovae are these massive explosions of stars that can be seen from very far away. I'm not going to go into much detail on how this analysis goes, but the groups of the High-Z supernovae team and also the Supernova Cosmology Project could observe that the universe expansion was not only going but accelerating. And I have two plots here to show you that kind of behavior. The one on the left is without that acceleration. You see that the universe is still expanding, so the distances are still increasing, but this curve is curved downwards, so the expansion is slowing down over time. But what they observed is that this curve is actually pointing upwards, so it is curving upwards, so this expansion is accelerating. What is driving that acceleration, we don't know, but we call it dark energy. Not literally dark, not because it's dark physically, but because we don't know what it is. It's some source of energy that is making the universe speed up, and we don't know what it is. And that's our goal here. That's the goal of DESI, and of course there are a lot of other groups in cosmology. But because DESI is measuring positions of galaxies, as I'll tell you about later, first I wanted to highlight how a 3D galaxy map could help us characterize the expansion of the universe and shed light on the mystery of dark energy. So we'll need one more concept to understand that, and that is the fact that the speed of light is finite. So I'm right there at the center of the universe. Of course, the universe has no center, but wherever I look, I am the center of the universe. That's philosophical, right? So notice that because the speed of light is finite, it takes time for light to reach me. That means I'm looking at the past of things instead of looking at their present. Of course, the distance between us here is like nanoseconds, right? The time that takes light to go from your faces to my eyes. Well, that's also philosophical. But because galaxies are very, very far away, it takes millions and billions of years for their light to reach us. So this is really an important effect in cosmology. And the further away you look, the further back in time you're seeing. So there is a time dimension whenever we're looking at galaxies far away. That means that if we measure separation between galaxies that are far away and compare that to separations between nearby galaxies, Because the universe is expanding, those separations tend to increase. So by doing a statistical analysis, we can track by how much space expanded from the time we're seeing those galaxies until now. Does that make sense to you? This is the essence of what DESI is doing. Great, so we just have to point out telescopes and map as many galaxies as possible, right? So I have this beautiful image here for you showing galaxies from the Legacy survey, and the Legacy survey is a collection of images from multiple other surveys. And once we have those images, we just run some code and extract some results on dark energy, right? Is it that easy? If I give you this image, can you figure out what dark energy is? No, right? Because there is one very important piece of information missing from this. What is it? The distances. Distances to these galaxies. I'm giving you a 2D image. How are you supposed to extract a 3D map of galaxies from it, right? So how do we measure distances to galaxies? For those of you who are fans of XKCD, here is a very nice comic. Cosmology news. New telescopes are finally powerful enough to read the little labels next to stars showing how far away they are. Of course, reality is not that easy, right? Galaxies don't have little labels next to them. So we need to use other methods, and the method that we use, and then I'm going to tell you about right now, is called Redshift. The idea is very simple. You're observing galaxies far away. We are here on Earth, and space between us is expanding. So light, which is essentially a wave, I'm going to draw a wave here, is being stretched along with the expansion of the universe. And because light is being stretched, its wavelength is increasing. And remember, the wavelength is the distance between one peak and the other peak of this wave. We usually call it lambda. And as the wavelength gets stretched, the color that corresponds to longer wavelengths is red. So that's why we call this a redshift, because the light coming from these galaxies is shifting towards the red direction. So we just have to analyze light coming from these galaxies and figure out by how much it was stretched. But how do we know that the original light that came from that galaxy got stretched? For that, I have a little demonstration for you here. I'm going to turn on this light. And you might have received a little diffraction grating. That's how it's called. And I also have one here in my pocket. And there is one equipped there in the camera. But the ones you have received have a little scale in it. Do you see it? In nanometers. So what this diffraction grating does is, if you look at some source of light through it, it will decompose that light into its multiple wavelengths. So you see a rainbow, just like in the image there. Can you see it with your own diffraction gratings? Super cool, right? Yeah. I'm glad you guys are going to keep this. You can do this at home too. Don't look at the sun with this. Of course. So this beautiful lamp here has a spectrum which is fairly continuous, as you can see. You go all the way from red, that corresponds to longer wavelengths, to blue and purple, which are shorter wavelengths. But now I am going to add, in front of this camera, these glasses here. They're made of neodymium, which is a material that is going to absorb light in very specific wavelengths. So what do you see there in the camera? You see some stripes, right? Black stripes. Do you see that? Vertical stripes. At very specific locations. So atmospheres of stars are the same thing, because there are elements in the atmosphere of stars that like to absorb light in specific wavelengths. This was well timed, thank you. And that's exactly the example I have here. So the light that we observe from galaxies come basically from the stars in those galaxies, so they will also present those lines, those absorption lines, and also some emission lines, but I'm not going into much detail on that. And fortunately, we know all these elements, and we know the specific wavelengths at which they absorb. So by looking at these specific wavelengths and seeing for nearby galaxies how much they get shifted, for distant galaxies observing that they get shifted even further in the red direction, and for very distant galaxies they are super shifted. Do you see that in the plot? So from this, it's fairly easy to determine by how much this light wave has been stretched. Are you convinced? Great, because this is basically what DESI is doing. We're measuring spectra of galaxies. And here is a very nice plot by Shadab Alam showing different spectra measured by DESI. The ones here at the bottom are for nearby galaxies, and the one at the top are for the galaxies that are the furthest away from us. And you see there are a lot of features in these spectra, right? And you clearly see the features are being shifted to the right, which is the direction of longer wavelengths. So I think this is a very nice compilation of what galaxy redshift is doing. Great, so let's talk about DESI. This is the Mayo telescope in Arizona, where the dark energy spectroscopic instrument is installed. So the Mayo telescope is at Kitt Peak National Observatory. That's very close to Tucson, for those of you who are familiar with the area. It's in the land of the Tohono O'odham Nation, and it's measuring 50 million spectra in the course of 5 years, and a couple extra because we're getting an extension. And the goal of DESI is essentially to look at all of these galaxies, select for which ones we want spectra for, and measure those spectra. But measuring spectra is kind of a tricky thing because it's very hard to do that just with an image like that. To get spectra with the accuracy that we need for our purposes, we need to take the light that comes from these galaxies and input that into spectrographs, which are big pieces of equipment that have complicated optics, and decompose that light and analyze that light. So we can't do that at the position of the telescope, at the focal plane. So we use something that you're probably familiar with, which are optical fibers. So instead of having a camera, we have a set of 5,000 fibers where the camera would go in the telescope. And then those fibers, you can see how the fiber works, right? It guides light from one end to the other. So those fibers will guide the light from the focal plane of the telescope all the way into the spectrographs. And that's what I'm going to be showing you in the animation here. So this is a telescope. Light comes in, reflects off the primary mirror onto the focal plane. In the focal plane, we have 5,000 fibers coupled to 5,000 little robots. So here you see the robot and the fiber in orange. And these robotic positioners can point the fibers at a position of each galaxy. And they're very efficient in doing so. So the fibers then run down to this lower floor where the spectrographs are, and the spectrographs analyze the light. Very cool, right? This is how the positioners look like in the focal plane, and fortunately, Michael Schubnell handed me one so I can demonstrate to you. It's about the size of my head, if you look at it. And oh, very nice, you can see through the camera. So here it is. So there are two X's. So there is this silver thing here, that is one motor. There's one motor here inside this shell. This black part rotates all together, and then coupled to that red part, you have a second motor, this other silver thing. And that can rotate the fiber that goes at the tip right here. At the bottom, there are a bunch of electronics. The Michigan M, if you want to be proud of Michigan, right? And yeah, so these positioners, you can switch back, I think. These positioners, they were developed and built here at the University of Michigan. And we are very proud of that. I'm going to show you in a bit a video of that happening. In this image, the fibers are being illuminated from the back. That's why you see a purple dot, right, in the position of the fibers. And the camera that is looking at the focal plane is keeping track of where all those robots are pointing at. This is a schematic of how it works. So as I showed you, there is a motor at the center that works like a shoulder. And then there is a second motor here that works like an elbow. So this little arm can point at anywhere within this circle. The patrol radius that each positioner can cover is about 12 millimeters. And the distance between the centers is 10.4 millimeters, so you can see there is some overlapping region. But don't worry, they're not going to collide with each other. People who implemented the algorithm that controls these things, they're very smart, and they keep track of the position of all of these robots at the same time. So what these fibers see on the other side is the galaxies, right? The image coming from the galaxies. And each of these fibers will be pointing at one galaxy within this region that is highlighted in blue. And these are how many targets we want to measure the spectra for in this part of the sky. So you can see that we have to visit the same region multiple times until we get all the spectra that we need. And you can actually see this in a website and drag around and zoom in and out like on Google Maps. I have a link at the end of my slides. You can, with the QR code, you can also access that whenever you get home. It's pretty cool. There are a lot of very beautiful galaxies. This is a comparison of how this process of measuring the spectra was done before and how we do it with DESI. So before DESI, we had the Slow and Digital Sky Survey. And what people would do is they would have these aluminum plates. They would drill holes at the position of each galaxy. And then somebody would have to manually plug in the fibers on each of these holes. And you can imagine that process took time, right? Something that we're now doing automatically within a few seconds. So within a few seconds, you have 5,000 positioners pointing at 5,000 completely new different objects to perform a new measurement. And the measurements take about 30 minutes to be obtained. So this is really impressive. And this is a video showing the positioners being assembled here at the university by a group of undergrads, engineers, staff, led by Gregory Tarley, Michael Shubnell, and other people. And we're very proud of this because this is really enabling us to go way beyond what we could do before with the previous technology. So, after all of this effort, we were able to build this beautiful catalog of galaxies that you see right now in 3D. What I'm showing you here are the galaxies that were selected for the cosmological analysis in the first year of data. So there are about 6 million objects here. We have measured more spectra than that. These are just the ones that have been selected for cosmology. And you can thank me later, but I made this available in a small simulation where you can fly through and pretend you're in Star Wars or Star Trek. Yeah. Of course, assembling this data is the effort of a big team. I just made it into a game because I think it's pretty cool. But what did DESI find by analyzing all of these galaxies? And you might have seen in the news hints of dynamical dark energy. What does it mean for dark energy to be dynamical? So there is this very interesting fact about dark energy that it was thought to have constant density. And that's very close to true. And that's kind of a bizarre thing to say because imagine, constant density means it doesn't matter the volume, the density is the same. So If you have particles in a box, and if you double the size of that box, the density is half of what it was before, right? Because the volume increased, but you still have the same stuff in the box. But dark energy doesn't work like that. The density is still the same, so the total energy inside that box would have doubled. Sounds weird, right? Sounds like a violation of energy conservation, but trust me, that violates classical energy conservation, but not in general relativity. But still, this is quite an interesting behavior for dark energy. And the way we usually parameterize the way something reacts to cosmic expansion is through an equation like this. So rho is the energy density of a component of matter, of light, or of whatever you're talking about in the universe. And rho naught is some reference density. So if the scale factor increases by some number, the density goes down by that number cubed because we're talking about 3D space. Does this make sense? Okay. So any deviation from this behavior is usually tracked by this W here. If W is 0, you get what you're used to. If W is not 0, you get something else. You get a different kind of reaction. And light reacts to expansion in a different way compared to matter. That's not a very bizarre thing. But for dark energy, we are very close to W of minus 1. W of minus 1 will give you an exponent of 0 here, telling you that the density doesn't depend on the scale factor. Does that make sense to you? So what DESI is doing is trying to detect deviations from that W of minus 1 that we use to describe dark energy. And our data so far suggests that W is changing over time. So in this plot right here, I have in the horizontal axis the value of W today, and on the vertical axis, the rate of change of that value. And this pink region is where we think the truth is. If the universe was what we call lambda CDM, so dark energy is described by a cosmological constant, for those of you familiar with that term, this pink contour would be centered at the position of this star over here. But do you see we get a considerable deviation from that? That is a hint that the way dark energy reacts to cosmic expansion is changing over time. So this is the first time we're starting to detect dynamics to dark energy, to try to understand a little bit better what it is made of. And I'm not going to draw any big conclusions out of this. I'll just leave you with this question. Will this evidence be confirmed with more data? We still have years of data to analyze and results to publish. So what do you think we will see? Well, I'm not going to commit myself to anything. I'll just wait. And I just wanted to leave you with this QR code if you want to access this very nice simulation that we have in the background. And just to really make sure you guys are interested in opening the web link, I'm going to fly around these galaxies just like in a video game. I think this is really cool. So if you want to access this yourselves, I suggest opening this on a computer and playing around. You can go to my website and you'll find all of that there. And, well, with that I conclude. Thank you so much.
Okay, thanks, Otávio. Thank you both for great talks with a dark theme. Okay, so we are going to bring this microphone. For those who would like to ask questions here, thank you, Monica. In the audience, we have, we're starting to receive questions from online as well. You can address questions to both, or either, of Otávio and Emilie. So actually, while we're getting ready here in the room, I wanted to make a note, and then I may just start with a question. So the note is, Emilie talked about direct dark matter, WIMP detection, actually, and the LZ effort. And so it's worth noting that we also have participants here at the University of Michigan in the LZ effort, and Professor Lorenzen and Hasselschwart. Okay. So let me start the discussion. This is, I think, a geology question, so we asked for some clarification. We haven't gotten it yet, but the question is for Emilie, and it is, do you ever use zircon crystals?
That's a good question.
And what are they?
Yeah, so zircon is actually the oldest mineral that you can find on Earth. You can actually find samples that are like 4.5 billion years old. I think I said the Earth was like 4.5. I'm pretty sure it's more like 4.7, so apologies if I made that mistake. But zircon is very radioactive in nature, so it has an incredibly high background of fission tracks and radioactive decay tracks. So it ends up being a mineral that would just really easily swamp the signal that we're looking for. But you can theoretically use zircon, yes. So, if that answers that.
Great,
yeah.
Thank you. And Otávio, why is dark energy energy?
Oh, wow, that's an interesting question. So dark energy, whenever we're talking about the expansion of the universe, that is something that is related to energy, right? Because components in our universe are usually described by their energy content. There is even like the famous equation that people simplifying Einstein's equations to get the E equals mc squared. So whenever you have stuff, that stuff has energy. And energy curves space-time, and energy influences the expansion of the universe. So because we have discovered dark energy through its interaction with the cosmic expansion, we name it dark energy because it is some sort of energy that is making the universe accelerate. I think that's a short explanation.
Okay. I could also ask why it's called dark matter, but that seemed more obvious. Maybe you want to address that.
Yeah, so dark matter does not reflect, emit, or absorb any light. So it was our super witty name to call it initially. We say it was dark because we couldn't see it. So I guess that's the short answer. It's invisible to us, so we just call it dark, as opposed to normal matter that will absorb, emit, or reflect light. So.
But it exerts gravity. Here's a question.
Yes.
If the speed of light is finite, then why, soon after the Big Bang, they say stuff moved faster than the speed of light?
So it's not a problem if you're looking at things that are far away. It's not a problem that you see that their velocity is faster than light, because you're not communicating any information at speeds that are faster than light. It's just the expansion of the space-time itself that is faster than light. So the problem with faster than light stuff is causality, right? In some reference frame, if some information travels faster than light, in some reference frame, you could see the effect happening before the cause. And that's what we call a violation of causality. So that doesn't happen in an expanding universe because there is no signal traveling faster than light. It's just the expansion of space-time.
If you're going the speed of light, if you turn on your headlights, will they shine?
If you're going at the speed of light, yeah, they will shine because it's all a matter of the reference frame that you're looking at.
If they're shining, they're going faster than the speed of light.
So in any reference frame, light will travel at the same speed, right? So if you are in your car, you would definitely see the light going at the speed of light. And also somebody who's not in your car who has some relative velocity with respect to that light will also see it traveling at the speed of light. So space-time will behave in such a way that you will observe the same speed of light everywhere. at any reference point. It's a bit tricky to visualize, but the equations work. Yeah, sure.
But there will be a Doppler shift.
There will be a Doppler shift, yeah.
Another question.
Yes, regarding the tracks that you find in these ancient minerals, how do you distinguish between the tracks that are created from normal radioactive collisions and the ones that are caused by dark matter?
Yeah, it's a good question. So the defects themselves are inherently identical. They are a string of essentially just, it's hollow cylinder, track-like shape, and it has like, it's amorphous shell. So kind of deducing the source of that track is going to be more statistical in nature. We're never going to be able to point to a track and be like, I know for a fact a dark matter particle created that track. They all look the same. They're just remnants of some sort of transfer of energy that happened. Sometimes, though, specifically radioactive decay chains, or maybe like a point radioactive source in the lattice, can have a sort of spatial symmetry. So sometimes using that type of method, you can say, like, we know that this was a radioactive process that created these tracks, but they're all going to look the same. There is also going to be, I didn't really talk about this, but the energy of that incoming particle that creates the track, that energy spectrum for all these different particles can overlap, and so they can create the same tracks that look the same but also have the same length. So it's going to be more like a statistical approach, I guess, is the best answer to your question.
Right, the energy that in the curves of the tracks indicates the energy of the incoming particle, and you can deduce the mass of the particle that came in. And if it doesn't fit any of the standard particles, then maybe you've got something interesting there.
Yes, yeah, so you do have a point. So there are some dark matter models that suggest that dark matter is just like this enormously massive particle, and in that case, it would just create such a large damage track that, like you're saying, nothing in the standard model could create. So that is like one aspect that we could rely on. On that note, something I just thought of as well that can help us distinguish the source of tracks is by like mitigating our backgrounds really well. So atmospheric neutrinos are a really good example of this. So these are neutrinos that are produced when cosmic rays enter our atmosphere, and those charged particles decay into neutrinos. But those tracks can be very long, like up to a millimeter in length, and there's not many other particles that extend to that range. And so if we can suppress, well, except for cosmic rays, so if we can suppress the cosmic ray background, there are certain regimes of energy or track lengths that we can say nothing else should create tracks of that length. And so we can say, those are atmospheric neutrino tracks, for example. So, yeah, of course.
I guess you can see here in it's not in the center, so the people online can't see it, but the people here can see that there are different kinds of tracks, right? The different particles just appear differently. The hard ones to see, they're these little, very light, I guess I would say, not big, thick, puffy things, every now and then. And sometimes even, as Emilie mentioned, wise. So, all right, here's another question. Yes?
This question is for Otávio. On your screen, you had two diagrams, one from the Big Bang, or both from the Big Bang. One showed the general curve without dark energy, and the other one showed this downward curve then becoming an upward curve. This particular curve, would that be the actual same curve if our visible universe was just a piece of the overall universe, and beyond this universe there were older galaxies from previous big so-called Big Bangs? And would that tracking be the same and would vary the way this tracking does depending on which part of the universe you're looking at, due to different densities of these older galaxies? I just want to know if that tracking would be the same for that situation?
Right. But that's a very good question. And there are people who look at whether we are in a very specific environment in our part of space such that we would see such behavior, right, for dark energy or for our specific expansion history. And the answer is, so far, we haven't detected any deviation from that. So it all indicates that our universe as a whole is expanding like that. It's not just like a tiny region, if I understand your question correctly.
Okay.
Yeah. So we're looking at, so statistically, we're mapping a big volume now in multiple directions, right, with DESI, and they all point at the same behavior.
One other quick question that led me to this was the Webb telescope. When they were searching for the very beginning of the Big Bang, they found very mature galaxies way out at that distances. Did you hear the same report as I did?
Yeah, so that's I think they're finding results that are very interesting for galaxy formation, right? Because they see galaxies at redshifts that we're still trying to understand how they formed
Now, if they weren't formed in the Big Bang, okay, would that mean that their gravity, for being so huge, is an attraction for particles in our universe instead of just this dark energy pushing it out?
Right, so these galaxies, they are pretty small compared to the whole universe. So, and also they're formed pretty late after the Big Bang also. Like, it is early compared to what we think galaxy formation does, but it's still pretty late compared to the Big Bang.
Okay, thank you so much.
Yeah, sure.
Okay, here's another question. It's probably for Emilie, but Otávio mentioned that dark energy now appears not to be uniformly distributed.
Uniformly distributed, but that it varies over time.
Varies over time.
Yeah.
I'm going to go back to the uniform distribution. Is dark matter also uniform?
No, it's not. So we actually assume, or we can measure, and we assume that there's like this halo of dark matter that kind of encapsulates galaxies. But there's kind of this like web-like, string-like structure of dark matter throughout the entire universe. We hypothesize that it's that underlying structure that actually helped galaxies form in the first place. Not every single galaxy has a dark matter halo, which is a neat key piece of evidence of why it could be an exotic particle. But the short answer is no.
And a couple of technical questions, I guess, one for each. This isn't so technical. Who digs up rocks 5 kilometers deep? Why?
So the question is like who here? Okay. So usually wells that are that deep are going to be like exploration wells for oil drilling. So there's no active mines that go down to 5 kilometers deep. That's very frustrating because I really want some rock samples from 5 kilometers deep. So it's typically like these exploration boreholes. So people will just bring out kind of a core of rock so they can see what's down at that depth. And usually it's like monetary like motivations. So that's how we would find rocks from 5 kilometers deep. I think the deepest active mine, I think, is just about 3 kilometers, maybe up to 4. It's either 3 or 4, but it's in South Africa. It's like a really deep gold mine. But no 5-kilometer active mines.
And then, Otávio, it must take quite a bit of care and computation to decide what order to look at the galaxies in. So there's 2 questions. One of them was, how do you select the particular sample of galaxies? And then how do you actually decide which one's first and second and third, how that process of moving the fibers works?
Right, so the first question is, how do you decide what galaxies to observe, right? And that's really, there is a task force to decide that because there are multiple possibilities. But there are a few important things that we always want from these galaxies. First, we need to easily observe those galaxies and make sure we can get spectra for them. So they usually have features in their spectra that we can focus on and reliably determine their redshifts. Another thing, we are interested on the underlying matter density. So not necessarily on the position of each galaxy, but on the density field that they are tracing. So that sounds a bit technical, but if you have questions on that, I can clarify. And some galaxies cluster more than others. So it's also important that those galaxies have high clustering so that you can really probe the density field that is underlying. Those are two things. Also, you have to make sure that those spectra, they have features that fall within your measurement range, so the range that you can cover with your spectrographs. So there are a number of decisions. And also, generally, you want to characterize well your sample. You need to know if you're missing galaxies or if you can measure all of them. So all of those things, together, they compose this decision that you have to make on what types of galaxies to aim at. I didn't really explain this, but there are some types that we usually focus on. Luminous red galaxies, emission line galaxies, galaxies that have very specific emission lines in their spectra. We have the bright galaxy sample, which is just a sample of very bright galaxies that are nearby. We have quasars. So there are specific categories that we focus on because of their properties. Yeah. And sorry, you asked about the order in which we observe. That's complicated. That depends on observing conditions on each night. If the moon is out, we can't measure dark objects. We have to measure the bright objects. So there is really a very well-designed algorithm that determines at each observation what galaxies we're pointing at.
How big, how many people are involved in DESI?
I would say 500, 600? 1,000 already? Wow, it's growing, yeah?
And are the data only available to the scientists taking part, or is it fully accessible?
Right, so it first becomes available to scientists in the collaboration, and then after we publish our main papers on that data, we release it to the public. So the data set that you see in the video that I showed is the first year of data, and that is public already. That's why I could put it on my website. Otherwise, I wouldn't.
I see.
But we already have the analysis of the first 3 years of data. So that data is not public yet, but we have results on that. And we're almost getting to 5 years, so pretty soon we'll have the initially planned survey complete.
And your team overall, Emilie?
Oh, at Michigan, it's me, one other grad student, and 2 undergrads, as well as the PIs, just 3 PIs. I would say in the greater collaboration of everyone, maybe like a couple dozen or something like that. Yeah, not very many. It's a very small group of us. This research is very new. So the first paper that was published trying to revamp this idea of using minerals as ancient particle, or as rare particle detectors was published in 2018. But we didn't really start like real work. Well, I did a little bit early during my master's, which was 2021 to 2023. But Michigan work started around 2023. So it's a very new field.
Great. And there's another question here.
What's the angular field that each fiber sees?
It's a good question. I had that number. So you want the size, right, that each fiber sees, so not the position or radius.
Right.
Michael Shubnell would have been very useful now because he knows that number.
So what's the angular field that they can move about if you don't know the...
That's also a question he would be able to answer. So I'm giving away that I work on a very downstream part of the analysis, right? So whenever I get to the data, it is already in the form of a catalog or like a table with a lot of lines.
Thank you.
But I can get you those numbers if you're interested.
It's probably available online someplace, is it?
Oh yeah, we can probably find that in like 5 minutes of search in the web.
If I search for it. Thank you.
Yeah, sure.
Okay, so here, a question to interpret the E equals MC squared in the context of changing energy or mass of the universe. So the question is, explicitly, if E equals mc squared, does that mean that the universe is losing mass? That question make sense to you?
Right. So why would it be losing mass? Because I think the obvious thing to me would be to
energy
think,
density is changing.
right. The total energy of dark energy would be increasing, right? But you could imagine well, yeah, I'm not sure, but what I would say is that energy conservation looks different in general relativity. So we don't talk about energy conservation separate from momentum conservation. There is an entity called the energy momentum tensor that is conserved as a whole, and that is still satisfied in an expanding universe. So that's what I would say. And it really has to be that way because energy conservation is a consequence of invariance of the laws of physics to translations in time. And momentum conservation is a consequence of invariance under translations, spatial translations. And in relativity, you know, time and space, they are this single entity called space-time. So you can't have those things being conserved separately in general. In general, you have a conservation of the energy momentum tensor. So yeah, for a tricky question, I have a complicated answer.
It takes a lot of courage to agree to a Q&A session sometimes.
Oh yeah.
And with that, I want to say that you can see what talent there is and how the future of science and scientific research is in great hands, and hopefully also an inspiration to the number of younger people that we have here in the audience. So it's really great and a privilege to finish a Saturday morning physics season with the Van Loo graduate student lectures, and these are two of the best we've ever had. So let's thank them again.